Hi everyone, today we're looking at Module 4, Lessons 16 and 17, and we're going to start computing the slope for non-vertical lines. So as you know, slope determines kind of the angle or the steepness of a linear equation. So in Lesson 16, we're going to focus on the computation of the slope of a non-vertical line. And non-vertical means, right, anything that's not a vertical line. So if the line goes straight up and down, that's not what we're talking about. We're talking about all other kinds of lines. And in this lesson, students will use similar triangles to explain why the slope m is the same between any 2 points on a line. So when we look at the slope, and what we kind of focused on our last video was that when you have 2 points, the slope is the vertical distance over the horizontal distance between those 2 points. But that's actually the case for all points on a particular line. I could pick any set of 2 points and I should end up with the same slope. And then we're also going to focus on how to compute the slope or how to actually solve for it. So what we want to remember is that the rate of change in a line is actually equal to the slope. So the rate of change we've talked about, that constant in some word problem scenarios where we think about how far a distance someone is traveling in a certain amount of time. But slope is very similar to rate of change because we're changing one variable and we're changing a second variable, and we just need to figure out what that change is. So there's several different ways you can write the slope. This third one here, the rise over the run, is what you're probably most familiar with. What that means is what vertical distance there was over the horizontal distance. And then that last one, the difference in y over the difference in x, that's kind of the most easy to compute mathematically. If, for example, your 2 points are really far apart, you didn't want to count them, or you didn't have a grid, you can just use the coordinate points and actually solve for the difference between those y values over the difference between those x values. And remember, the difference is the answer when we subtract. So we're looking at an example. I'm just setting up this graph quickly to determine the slope of the line. So I plotted 2 points. One was at 1, -2, and one was at 4, +7. And thinking about the slope, I want to see what is the vertical change over the horizontal change. Now I picked that point on the line to start because it goes through a nice intersection of my grid paper. I don't want to pick a point that I can't measure accurately. So once I have this determined, I can draw what's called a slope triangle and show that vertical distance of 3 and that horizontal distance of 1. But then I can repeat that triangle down my line and determine that slope is consistent throughout a linear equation. So no matter where I am on that line, I should be able to get from point A to point B with a vertical distance of 3 and a horizontal distance of 1. Module 4, Lesson 17 says the line joining 2 distinct points. Now, again, when we're looking at a linear equation, we're looking at a line on a graph. The slope of a line joining 2 distinct points has a slope which is equal to m. And when ax plus by equals c, that's the same as saying y is equal to -a over bx plus c over b. I just manipulated that equation to change the order of the variables, and I did that using properties of equality. But what I want to show you is how slope works with similar triangles. We all know that when we have two similar triangles, the corresponding sides are proportional, and we can write a proportional equation from that. But when I look at a linear equation and I use my either y values or x values to draw some parallel lines, this brings us back to the fundamental theorem of similarity, which was in Module 3. So when we have similar triangles, I know that slope is equal to m because I have those two angles that overlap by the origin. I have two right angles, so I know my triangles have to be similar. And so the ratios of the corresponding sides are going to be equal. So I get y over m equals x over 1. And when I solve that, I get y equals mx, which is my slope.